Hello and welcome to part 3 of Dev Maths and Stats course lecture 2, where we come to these rules in these two sections here. Now before we begin, to understand where these sections fit into the overall lecture, if you imagine that instead of talking about maths, we are talking about driving a car or using a mobile phone, then the first part here is the concept of derivative. So that's why do you need a car, what's it for, and why would you want a phone, what are you going to do with it? That's quite essential to know that. Then this section here is how they're found from first principles. This is how does a car work and how does a mobile phone work. And it could be useful to understand that, and you should have some idea about it. You need to know to put petrol and fuel in the car. You need to know that you're going to charge the phone and maybe update the operating system and the apps and not drop it onto concrete like I did with mine the other day. But really, for everyday use, it's good if you know that, but it's not essential. But then we come to these two sections here, which are about how do you drive a car, what's the accelerator, what's the steering wheel, which buttons do we press to unlock the screen of your phone and dial a number or call up from favourite app. So these are the things really that you need to know, and this is going to be the same in maths. This is the total bread and butter stuff that you will meet a lot this year and in future if you work with anything mathematical in the social sciences. So let's start with this first section, differentiation rules for simple functions. So I'm dividing this into two parts. There's simple rules that we can use for polynomials and for exponential and logarithmic functions. So we'll start in this short video with the polynomials. So expand that section. And by polynomials, remember, we're talking about functions like x squared, x cubed, 5x squared, and so on. So the general form for a function in x that's polynomial is a, which is a constant, so it could be 5, 3, 7, 1, negative 12, times x to the power, and it could be to the power 1, 2, 3, 4, 5, and so on, or any number, as we'll see. So the rule is that if a function of x is a x to the power n, then to differentiate f dashed of x, the derivative function is a n times x to the power n minus 1. So you multiply by the n and then reduce that n by 1 to get the derivative, to get f dashed. So quite simple to see this with some examples. So in the red maple language, this is 6x to the power 3, and this means differentiate the last thing, which is that, and x is the variable we're using. So 6x to the power 3, and we get 18x squared. So you can see that 3 times 6 is 18. 3 subtract 1 gives you 2. So with all of these, as I go through them, you should be pausing the video, checking that you can predict what the derivative is going to be. So here we have 2x to the power 9. I'm going to differentiate that, so you should predict what it's going to be. And it's going to be 18x to the power 8. 2 times 9 is 18. 9 goes down to 8. Here we've got 5x. How am I going to differentiate that? It looks quite simple, 5x. Try to predict the answer. The clue is that 5x is the same as 5x to the power 1. So that becomes 5 times 1 is 5. X to the power 1 goes down to x to the power 0, which is 1. So what looks like a simple rule suddenly becomes a little bit harder, but you have to imagine there's a 1 here, so 5 ones is 5. X to the power 0 is the same as 1, so it's 5 times 1, which is 5. Try and confuse with a bigger number, 14u to the power 10. Okay, 140u to the power 9. Here's 145 differentiated. Now, to think about what the answer might be here, think about the interpretation of this one, 5x. If you imagine this on a graph, y is equal to 5x would be a straight line. The gradient of that straight line everywhere is 5. It doesn't change, which is why there's no x in this derivative. Unlike these, where they're getting steeper and steeper as you go up with x. So here, the gradient is always the same. It's 5 everywhere, so it's a straight line. Now if I draw the graph of y is equal to 145, what is the gradient of that curve everywhere? That should help you get the answer. So try and think what the answer is going to be. And yeah, we do that. 145. it's just a fixed number because it will be a straight horizontal line. Okay, so far so simple. Seems to have got, let's see if this works. This one here, 5x to the power minus 3, differentiating that now, apply exactly the same rules, think carefully about exactly what it's going to be. So try and predict, and let's see if you get this, and see if this actually does. Okay. So 5x to the power 3 can also be written like this. So x to the power negative 3 means divide by x to the power 3. So when you see this, when you want to use this rule, which I've given you up here, you have to remember that 5x to the power 5 divided by x to the power 3 is equal to 5x to the power minus 3. So you have to remember that 5, when you see this, this is exactly the same as 5x to the power minus 3. So when you want to differentiate, this, you apply the rule, which is negative 3 times 5 is negative 15. And then x, that negative 3 becomes negative 4. So this reduces to negative 4. Then this is correct, fine, but if you are working in this format, do you want to change this back to this format? So this is negative 15 divided by x to the power 4. So when you become more advanced and you are used to this, you can take this and straight away differentiate to this. But it is very easy, and I often do it, to make a mistake. You get the wrong negative, the negative sign is positive instead of negative. It's easy to make a mistake here, and also it's easy to change this to 2 instead of making it go down to 4. So if you're not sure, change it to this form and then differentiate, and then change back to this form. Then we come to similar things where we have fractional power, so 2x to the power half. So 2x to the power half, you have to remember that x to the power half is the same as square root of x. So this is the same problem as differentiating 2 times the square root of x. So if you see this problem, you want to differentiate it, you must remember it's x to the power half, then 1/2 times 2 is 1, and half becomes negative half. So this is the same as when you see this, those two things are the same. So to differentiate this, use the rule 1/2 times 2 is equal to 1. It's supposed to be a 1. And then 1/2 becomes negative half. So this is what you get if you apply the rule. So 1 times x to the negative half. Then that's the same as just 1 divided by x to the power half, which is the same as 1 divided by square root of x. So again, when you are experienced, you can just change from this to this easily, but it's very easy to make mistakes. So if you want to check, you go from here to here and check these numbers, check this, and then convert back to this form. Okay, remember that you are very welcome, if this is very, very easy, to fast forward. If it's too difficult, you can slow it down and go back and see it again, and ask me questions in the live sessions. So another similar one here. This is the kind of thing you will see a lot with the Cobb-Douglas production function. So 4 times p to the power 2 over 5. 4 times 2 over 5 gives you 8 over 5, which is this fraction. And then power positive 2/5. 2/5 subtract 1 is negative 3/5. So p to the power negative 3/5 means divide by p to the power 3/5. That's what you come to here. And then the last one, 12b to the power negative quarter. So 12b to the power negative quarter is the same as 12 divided by b to the power quarter. So that's the original question in a different form. And then differentiate. This is negative a quarter, so negative 1/4 times 12 is negative 3. And then negative 1/4 goes down by 1, become negative 5/4. So again, please ask me about any of these if you're not sure what happened there in the live session. Just a couple more examples, just to introduce this different notation here. So this notation means differentiate when the variable is x. You'll see that a lot. So previously I was using the f dash to mean differentiate. An alternative is to use d by dx to differentiate. So if this is y, dy by dx is differentiate y with respect to x. But the rules we use are the same. So if y is 7x power 3, then dy by dx is 21x squared, using the same rule. And finally, just to show how this works when you have different letters. So if e is equal to minus 4 times w to the power minus 5, so perhaps e could be some sort of exports or something, and w could be welfare or wage rates. So here's a connection between these two, and you can differentiate it like this. So if e is equal to negative 4 divided by w to the power 5, then dE by dW is equal to 20 over w to the power 6, using the same rules as above. And then the nice news is, if you can remember all of these, well, there's only one rule. Yeah? If you can remember this rule and how it applies in all these cases, the easy cases, the negative number cases, the fraction cases, once you have understood all of that and practiced it, then it's very easy to do cases like this when you have things added together, because you just do each one separately. So when you see this, you just apply the rule to each one separately. So here, 3 8s are 24, x to the power 7, 4 9s are 36, x to the power 3. And similarly here, you go through each part term by term. So this is the 16r cubed, minus 21 r squared, 2r, and this is a constant which is flat, has 0 gradient, so that disappears. Okay, so those are the first of our basic rules for polynomials. The other kinds of functions you meet a lot are exponentials and logarithmic functions, so we'll cover the methods of the rule for differentiating those in the next video. So thanks for watching.